So DeBroglie, however you like to say his name, I believe it's properly pronounced DeBroglie, but I say DeBroglie. DeBroglie, apologies to him, in 1920 said, okay, so we understand that the photon has energy E is hf, we wrote this down last time, which is equal to hc over lambda, and the momentum of the photon is h over lambda. So this was for a photon, and then scientists up until 1920 have well established light has both wave-like properties, diffraction interference, and particle-like properties, as shown here. So DeBroglie said, maybe we can. He was very versed in the quantum mechanics of the time, of the work of Planck and Einstein, and said, well, if photons, if light has both wave and particle-like properties, maybe matter has wave and particle-like properties too. So we should. So he just surmised that electrons also have wave and particle-like properties. So we already know the electron. We've always treated the electron like a particle. That was really J.J. Thomson's discovery of the electron. Was the electron is a particle and it's got particle properties. But DeBroglie said, oh, well, maybe the electron also has wave-like properties. If it has wave-like properties, then the electron, like the photon, would have a wavelength. The wavelength of the electron is equal to Planck's constant divided by the momentum of the electron. So this is what DeBroglie brought to us, is he applied this to electrons. Applied what we had found for light to electrons. Said, maybe they act like waves, and therefore that could help explain the Bohr atom, or it could modify the Bohr atom. It doesn't really explain the Bohr atom so much as it modifies the Bohr atom and explains the idea of quantized orbits. Because imagine the electron going around a nucleus. So let's say we've got a nucleus here. Right, here's our nucleus, and the electron is going around the nucleus. Here's our electron. And if it's a wave going around the electron, Okay, if it's going around, but it's a wave, so it would look something like this. I'm trying to make a wave go around in a circle. Now look what happens when I get around. If I had drawn that, so the electrons, which is, if we treat it like a wave, and if it's a wave, but the wave is going in a circle, if I were to draw that with a constant wavelength, it doesn't match up. And so it would destructively interfere with itself. So it's not allowed at that radius. So instead, there are going to be allowed radii where the electron constructively interferes with itself. Let's just see if we can draw a picture like that, or I'm going to fake it. So here's an electron. Try to draw a constant wavelength. That I've already messed up. But, whoops, already messed up. Oh, that destructively interferes with itself. It doesn't match up with itself. Would have drawn one. So the electron, again, is the wave, and let's just go ahead and trace over this with a different color. So if I drew it right, and if it matches up with itself, there, it is constructively interfering with itself, so that's an allowed orbit. Right? That radius is an allowed orbit. It's not allowed in orbits where it destructively interferes with itself. It is allowed in orbit where it constructively interferes with itself. So what are the wavelengths of the allowed orbits? The wavelengths of the allowed orbits are going to be where when it goes around the full circle, 2 pi r is the circumference of the full circle. So when it goes around the full circle, if it comes back, if it's off by 1 lambda, or 2 lambdas, or 3 lambdas, it's going to match up with itself. Is off by anything else, it's not. So what we've got, the condition n lambda equals 2 pi r, are the allowed orbits. It's a fantastic assumption DeBroglie made. And let's just see how that works out for the Bohr atom. So just rewriting that here, the assumption for allowed orbits, we said that the wavelength is going to be p over I'm sorry, not P over H, but H over P. H over P, like for a photon. And so therefore 2 pi r equals n H over P. And so therefore r times P is equal to nh over 2 pi, which equals nh bar. And what is r times P? R times P is the angular momentum. Angular momentum equals nh bar. Remember that, right? That was Bohr's condition. Bohr's condition for the quantized orbits. He just said, I don't know why, but the angular momentum is quantized. And it's DeBroglie who shows this is why. It's because the electron's a wave. So this assumption now explains the Bohr atom. Okay, so now we've got a modification, which is the electron acts like a wave. So is this true? So now we're gonna look at some other things where we say, oh, actually, matter does act like both waves and particles, just like light acts like waves and particles. But why do we not see this? Why do we not see matter acting like waves? We say in the lives we live, we know matter is particles. Matter's made up of particles. What are you talking about? Matter's made up of waves. And that's because the wavelength is so small that we can only see it in the extremely small, right? We only see it in the subatomic. And it's this idea that I spent so much time talking about, trying to explain, where diffraction, the wave-like property, is only observable, only normally observable if the size of the slit is like the size of the object. And the fact is that the wavelength of the electrons is so small that on a macroscopic scale, we just don't, it's not appreciable. We don't see the interference and diffraction because the wavelength is so much smaller than the objects that we interact with, the wavelength of matter. So, for example, what is the wavelength of an electron in the Bohr hydrogen atom and ground state? What's the wavelength of that electron? So we could go look it up, right, the V as a function of state, but we can just go ahead and re-derive it. The Coulomb Force Law, Ke squared over r squared, is equal to mv squared over r for the atom in the ground state. So therefore, I'm sorry, for an electron. That's not the atom in the ground state. That's for the electron going around a nucleus, and where therefore v is equal to square root of Ke squared over mr. Remember the radii are in the Bohr atom are indeed quantized, but let's just take the Bohr radius, right, that ground state radius, which is approximately 0.5 angstroms. That's just what we had figured out when we were doing the Bohr atom. And so therefore the velocity, the speed, can be given by plugging in K, plug in all those things with, I'm doing it in MKS units. It probably make more sense to do it in EVs, but anyway, let's just do it this way. If I plugged all those numbers into my calculator correctly, I get V equals 2.25 times 10 to the 6 meters per second. So therefore, mv, which is the momentum of the electron, is equal to 9.1 times 10 to the minus 31 times that. Okay, so let's see. So we had the velocity, mv, 2.04 times 10 to the minus 24 kilogram meters per second. Plug that in, look up Planck's constant, 6.26 times 10 to the minus 34 in MKS units. And we end up getting that the wavelength of the electron in the Bohr ground state is 3.2, not times 10 to the minus 10 angstroms, but 3.2 times 10 to the minus 10 meters, which is indeed 3.2 angstroms. Ah, look at that. So remember, we said that the wave nature is appreciable if the size scale is the size scale of the object or the opening or the whatever it's going through or around is around its own wavelength, and that is indeed a reasonable size scale. So the wavelength, so the electron, we can see the wave-like properties of the electron because the electron has a wavelength. If I calculated it correctly, might have made a calculated error of 3.2 angstroms. But let's ask another question. Why do we not observe this on a macroscopic scale? Let's ask, what is the wavelength of The DeBroglie, and we call it, when we're talking about matter, we call it the DeBroglie wavelength. What is the DeBroglie wavelength of an airplane traveling at 500 miles an hour? Well, the momentum of that wavelength is mv, so we need to know the mass of an airplane. Look up the mass of an airplane. I don't care how big the airplane is. Let's say that it's 10 to the 6 kilograms, seems reasonable, times 500 miles an hour. Well, put it in meters per second. That's about 250 meters per second. We're just getting approximate numbers here. So therefore, the wavelength of the airplane, the airplane will diffract or interfere when it encounters objects that are about its wavelength. But the wavelength, the de Broglie wavelength of the airplane, if we want to treat it like a wave instead of a particle, an airplane is an awfully big particle, but what is it in terms of waves? It's going to be h over 2.5 times 10 to the 8th kilogram meters per second. And so h is 6.626, 6.62 times 10 to the minus 34 meter squared kilogram per second. And so we divide that by 2.5 times 10 to the 8th kilogram meters per second. At the wavelength of the airplane is about 2.5. I didn't use a calculator. It's approximately 2.5 times 10 to the minus 42 meters. That's pretty small. So the airplane, it doesn't look like a wave to us, but if it interacts with, if it tries to go through an opening this small, it might diffract through that opening. Of course, it's going to plow through the wall, but you know what I mean. That wavelength is too small for us to see the wave-like properties of the airplane. That's the point. So we can diffract a particle if its wavelength, or we can interfere a particle if its wavelength is as large as the opening that we put it through or the object that we put it through. So you can, talk about a person walking through a doorway. Will a person diffract when they walk through a doorway? You can figure out their wavelength, and you're going to find that their wavelength is much, much smaller than the doorway, just like we did here. It may not be quite this small for a person because a person has a smaller momentum. But the wavelength is too small to notice the wave-like properties of a person. It's too small to notice the wave-like properties of a baseball. It's too small to notice the wave-like properties of a speck of dust. But when we get to the subatomic, when we're looking at electrons, neutrons, protons, then when we put them into boxes that are about the size of their wavelength, we actually see the wave-like properties of these particles. So the beauty of the de Broglie wavelength, the de Broglie wavelength, is that lambda equals h over p now explains, if we apply that to particles, it explains the quantized Bohr orbits, and it really brings together the Bohr atom with the de Broglie hypothesis. And so now we just have to prove that particles really do have wave-like properties, because de Broglie did not prove that. It comes to the Davis and Germa experiment, which we'll talk about next. Davis and Germa experiment is 1925, not German, but Germa, where they showed the wave-like properties of electrons by scattering them off of crystal surfaces like the Bragg scattering. That comes next.